Hello chemistry students, Dr. TΔrS here, and in this section we are going to do some calculations of free energy changes for a reaction. We will use Gibbs's free energy equation to assess the effect changes in temperature on the favorability of the reaction, and then relate Gibbs's free energy and the equilibrium constant for a reaction. Remember that Gibbs's free energy is a state function because both enthalpy and entropy are state functions. Therefore, we can write this equation and we can use our thermodynamic data to get those values. The thermodynamic data will be in your resources right along with your enthalpy and entropy values. For example, let's use our Gibbs's free energy thermodynamic data to calculate Gibbs's free energy for this reaction. I have 4 NH3, so ammonia plus oxygen, to give me 4 NO2s and 6 moles of water. I need to look up the gas states in all of these. So I'm going to take the sum of my products, it is mole dependent, minus the sum of my Gibbs's free energy values of the reactants, again, mole dependent. So 4 times the Gibbs's free energy value of NO2 plus 6 times the Gibbs's free energy value of water minus 4 times the Gibbs's free energy value of NH3 is our reactant, plus 0. We could say 7 times the value of O2, but you'll see that oxygen is 0. When I plug in those values, I would get a Gibbs's free energy value of negative 1,101.14 kilojoules per mole. This is a negative value. It is a spontaneous reaction and it is product favored. Now here we want to find the standard free energy change, Gibbs's energy, for the formation of methane from carbon and hydrogen using values of enthalpy and entropy. So first thing, let's look up the values of entropy and enthalpy for carbon and graphite form, for hydrogen gas, and for methane gas, because we're not just doing Gibbs's free energy of products minus reactants. So here I'm going to find delta H. Delta H, I found that I had a 0 for carbon, 0 for hydrogen, and a negative 74.9 for methane. So I'm going to do 1 times methane's value minus 1 times 0 and 2 times 0, which is 0. So I found my delta H. Now let's find entropy. Using the values from our appendix, I found the change in entropy, products minus reactants. So I found my delta S. Now delta S, the units is joules per Kelvin mole. I turned it into kilojoules so that my units would match. And then I'm going to plug it into my Gibbs's free energy equation where G is equal to H minus TS. I took my H from up above, minus my temperature. My standard temperature is 298 Kelvin. Maybe you use 298.15. It's okay, it doesn't matter. Times, and then I plugged in my entropy in kilojoules to find Gibbs's free energy of negative 50.9 kilojoules per mole Kelvin. It is a negative value telling us it is product favored. Here's a similar question. Using values of enthalpy and entropy, find delta H and delta S to calculate the free energy change for the formation of 2 moles of ammonia from the elements at standard conditions. See if you can plug those in. Let's see how you did. I took values from the appendix for enthalpy and entropy for N2, H2, and NH3. To find delta H, I did products minus reactants. 2 times the value of NH3 minus, this is 1, so 1 times 0, and 3 times 0, so that would be 0. I got a delta H value of negative 91.80 kilojoules per mole. For entropy, I did 2 times my entropy value minus 1 times nitrogen's value plus 3 times hydrogen's value. Again, that's in joules. I made it into kilojoules, so negative 0.1981, and then plugged it into Gibbs's equation. I plugged in my H from up above, minus, I used my 298 Kelvin, times the entropy that I found. And I got a Gibbs's free energy of negative 32.8 kilojoules per mole. It is negative, telling me it is product favored. This problem wants us to calculate the standard free energy change for the combustion of 1 mole of methane using values of standard free energies. So we're using the G values in our thermodynamic data, looking at the combustion of 1 mole of methane. How would you write that out? Well, 1 mole of methane is CH4. If it's a combustion reaction, that means that oxygen is the other reactant, and our products are CO2 and H2O. You need to balance this reaction, and then you need to find the thermodynamic data that would go along with it. See if you can find it. After balancing this reaction, hopefully you got a 2 in front of oxygen and a 2 in front of water, found the values in the back of the book, and plugged in my products minus reactants. I got a value of negative 800.8 kilojoules per mole, telling us that it is product favored at equilibrium. This problem wants us to calculate the standard free energy change for the oxidation of 1 mole of SO2 to form SO3. So if I have SO2 and I need to form SO3 and it's being oxidized, that means oxygen is my other reactant. And obviously if I have SO2 here and I want to get to SO3, I only need 1 more oxygen. So I'm going to have that as a half of an O2. See if you can find those G values and find delta G. How did you do? Did you find those G values and then plug it in and do product? So 1 times negative 371.04 minus 1 times the SO2 value plus 1/2 of O2's value to get negative 70.91. Looking at our equation here, our G is equal to H minus TS. That's the definition of Gibbs's free energy. That indicates that free energy is a function of temperature. So delta G will therefore change with temperature. A consequence of this temperature dependence is that in certain instances, reactions can be product favored at equilibrium at one temperature and reactant favored at another. Let's say a reaction has a positive delta H and a positive S. Then at high temperatures, we will have a spontaneous reaction, which means it's product favored. If I have a negative enthalpy and a negative entropy, at low temperatures, we would have a negative G, which is also telling me it's spontaneous and product favored. When Gibbs's free energy value is a large negative number, the reaction is spontaneous as written, and those reactants transform almost entirely to products when equilibrium is reached. When that delta G is a large positive number, the reaction is non-spontaneous, and the reactants do not give significant amount of products at equilibrium. When delta G is a small negative or a small positive value, the reaction gives an equilibrium mixture with significant amounts of both reactants and products. Here we have a decomposition reaction to produce nickel metal and carbon monoxide, and it's telling me a delta G naught value of 40 kilojoules per mole for the reaction at 25 degrees Celsius. So this is at standard temperature. It's telling me it's standard delta G. Use the values of delta H and S for the reactant and products to estimate the temperature at which the reaction becomes product favored at equilibrium. I need to find T, and at equilibrium, G is equal to 0. So I looked up the data for enthalpy and entropy for those 3 reactants and products. I calculated delta H and delta S. I didn't show the work because I assumed you could do the products minus reactants as we've done so many times. And then I plugged it into my Gibbs's free energy equation using 0 for my Gibbs's free energy because 0 would tell me that we're at equilibrium. I plugged in my H and I plugged in my S. Calculating T, I found that at 379.5 Kelvin, or if you subtract 273.15, we would say at 106.3 degrees Celsius, we would have a spontaneous reaction, which is product favored. Pause the video here to estimate the temperature required to decompose mercury oxide into mercury and oxygen, just like we did in the last problem. I did the same thing, setting my G to 0, found my delta H and my delta S from the thermodynamic data in the appendix, and found T would be 839 Kelvin, or if I minused 273.15 or 273, I would get 566 degrees Celsius. Let's dive into when we have non-standard states, which means that we are at a pressure that's different than 1 atmosphere or a concentration that's different from 1 molar. We use this equation from the last section. Q is our thermodynamic form of the reaction quotient, and delta G represents an instantaneous change in free energy at some point in the reaction approaching equilibrium. At equilibrium, G is equal to 0, and the reaction quotient Q becomes the equilibrium constant K. We rearrange this equation to get this, and we said in the last section, when K is greater than 1, the natural log of K is positive, and delta G naught is negative, so it's spontaneous. When K is less than 1, the natural log of K is negative, and delta G is positive. If I looked at thermodynamic data and calculated delta G for this reaction, I would get negative 4.8 kilojoules. That tells me it is a spontaneous reaction, which is product favored, and I would have a K greater than 1. Also telling me that I have more products than reactants. If I flip this reaction around, these are my reactants and this is my products, delta G would just be flip-flop. It would be positive 4.8, telling me that it's a reactant-favored reaction. K is now less than 1, and I would have more reactants than products. Here we're told that we know the value of K for silver chloride in this reaction, which is 5.56 times 10 to the 9th. Determine delta G for this process at 298.15 Kelvin. Well, we're going to use this equation, negative RT natural log of K. Since we're given K, we always know the gas constant, and we were told the temperature. Note 2 things. I can plug in my R 8.3145 as it is, but just make sure that you realize that this is a joules unit, and delta G is always in kilojoules. So you can do it as is, and then when you get your answer, divide by 1,000, or you can immediately turn your 8.3145 into kilojoules by making it 0.00833145, and that would be kilojoules per Kelvin mole, and then you would directly get that answer. It's a negative number telling me that it is product favored at equilibrium. This wants us to determine the value of delta G for this reaction from the data that's in your appendix, and then use that result to calculate the equilibrium constant. This one's a little tricky to work backwards and find K. Let's do it together. I took the G data for carbon dioxide, and for carbon monoxide, and I found delta G. Pause the video here to make sure that you understand how I found delta G. Once I knew delta G, I plugged it in here. I know R, I know T, but I have to solve for K. So what I did was I plugged in my R and I plugged in my T, I multiplied them together, and I divided both sides by that answer, which gave me negative 48.4 is equal to the natural log of K. To get K by itself, we have to do the inverse of the natural log, which is e raised to that number. And if you plug that into your calculator, e raised to the negative 48.4, we should get a K value of 9.41 times 10 to the negative 22. You could do it all in one process if you want to set it up like this. K is equal to e raised to the, notice that I took my G value divided by R times T, and I gotta have that negative in there because that negative is before the R. So the whole thing is negative G divided by RT. Pause the video here to try to solve a similar problem. Notice that using thermodynamic data, I solved for delta G. I then plugged that answer into my delta G in this equation. I put in my R, I put in my T, and then I solved for K. And I used that same equation from the last slide just to show you how I did it. So e raised to the negative, I plugged in my negative 70.70 divided by, I changed my gas constant into kilojoules right off the bat and times it by the temperature. And I got a K value of 2.4 times 10 to the 12th, which is a huge number. Now delta G is a negative number, so it is product favored, and K is greater than 1. It's a huge number, as it should be for such a process, telling me that if I have a K greater than 1, it is a product favored reaction. Pause the video here to solve this problem. First, it wants to know if it's a reactant favored or product favored reaction at equilibrium. So I needed to find delta G because if it's a positive or negative value, that will tell me if it's reactant or product favored. Delta G ends up being a positive 30.79. Since it's a positive value, it's reactant favored. Then it wants us to calculate the value of Gibbs's free energy for this reaction if my reactants and products are at values that are different than standard conditions. So it's different than 1 atmosphere. So I would take my Gibbs's free energy that I just calculated and plug it into this equation to find Gibbs's energy that's at a non-standard state. So my 30.79 that I just found plus my R, again I need it to be in kilojoules or I need that to be in joules, times T times the natural log of K. Remember that K is products over reactants. And the products, the iodine and the chlorine, we were told that iodine and chlorine were both at 1 times 10 to the negative 3 atmospheres, and the ICl was 1 atmosphere. So when I plug in my products over reactants, make sure that your reactant is 1 atmosphere squared because there's a 2 in front of it. Plug all of that in to get a delta G of negative 3.44 kilojoules per mole. This reaction will proceed spontaneously because it's negative until the reactant favored equilibrium is reached. Because up here we saw it was reactant favored, but down here it was negative, so it will be spontaneous until that reactant favored equilibrium is reached. Pause the video here to try a similar problem. Again, I used thermodynamic data to solve for G. G, a standard state, is going to be a positive 173.2 kilojoules per mole, which tells us it's reactant favored. It is non-spontaneous. But notice that in part 2, when I take the pressures given of those reactants and products that are at non-standard state and plug it in to find my G at non-standard state, I also get a positive number telling me that it's not spontaneous. Double check your work and make sure that you get the same as me. That wraps up this section. Here's a little summary table for you to look at, and that wraps up our chapter.